By the end of this lesson, you should be able to solve differential equations using separation of variables. So a differential equation is just an equation with a derivative in it. So for example, dy dx equals 3x squared. That's a differential equation. And generally, when we're working with a differential equation, we're asked to find the general solution, which is just the equation whose derivative is given here. This just means take antiderivatives so no dy dx's are left. So for example, find the general solution of dy dx equals 3x squared. Well, we know that y is the antiderivative of dy dx. So we just have to take the antiderivative of 3x squared. That's 3x cubed divided by 3 plus c. This plus c is going to be incredibly critical in this unit. So make sure not to forget it. These cancel out. So that, as you notice, we've already done before. Why are we spending a whole nother unit on it? Because this unit introduces a twist. What makes this unit different from the previous ones is that now we have situations where the rate of change of a quantity, so that's the derivative, right, depends on the value of that quantity. In particular, this is very, very frequently used for population. So for example, how quickly a population grows depends on the number of people or rabbits or whatever's in that population. So if you only have a group of 10 people, a population isn't going to grow very quickly. A group of 10,000 people and the population is going to grow a lot more quickly. So for example, we might have a situation where dy dx is like 1.5. Why? Notice that these match. Instead of this variable and the variable in the denominator like we had up here. Notice this is x, this is x. In this case, this is y, this is y. Once this happens, we need new techniques. Now, there are whole classes on differential equations at the college level. For our purposes, we're just going to introduce a basic method for solving them that's called separation of variables. So I'm going to put the steps over here. I'm going to do an example problem over here. Write the derivative in dy dx form if it isn't already. So let's say we have this dy dx equals 2x over y. There's an example problem. Separate the variables. This means put all of one variable on one side, all of the other variable on the other side. In this case, we're going to treat dy and dx as separate expressions. So when we're separating our y's and our x's, we're separating dy and dx as well. So like right over here, we want this y and this x to be separated. So if we multiply both sides by y, then the y goes over here. And now here's the part where we start doing things differently. Notice we still have an x here on this side, on our y side. We don't want the x on that side. We want the x over here. So just like I multiplied both sides by y to sort of cancel out the numerator over here, I'm going to do the same thing with dx. I'm going to separate this dy and this dx. This is the separation of variables step. Now we can take the antiderivatives Remember how our antiderivative always went with a dy or a dx or a dt or some sort of variable? That d whatever is already there. We just pop the integrals in front. And once we've done that, we can take the integrals like normal. Our fourth step, solve for y if possible. Now, one of the key things to be aware of is that c is a constant. We don't care what it is. It just is a number that could be any number. We don't really know. And because it could be any number, c plus c is still any number. C times 2 is still any number. These c's can be recombined, added to each other, divided, multiplied, subtracted, the works, these c's can be completely recombined and still stay as c. If you want to, you can number them like c1, c2, c3, all that kind of thing, but they just need to be something along for the ride. So for example, we could write this as y over 2 squared plus c1 equals x squared plus c2. If I subtract c1 from both sides, this is just some other constant. It's still any number. We don't know what it is. We've put these together. We still have a c. So the subscripts are optional. We can also just do subtract c from both sides. We still end up with c. It's a different kind of variable. I'll leave the subscripts because I think that makes things clearer for people, but you don't have to use them. Okay, so we're going to multiply both sides by 2. Two times c is still yet another c. And then we can take plus or minus the square root. Or right like that. Now notice that this is actually not all that different from what we've done before. We just sort of didn't show it. So like up here, if we imagine doing separation of variables, this should have a dx. Then really what was happening here is that we just multiplied both sides by dx to get that dx over here, took the antiderivative here just like normal, and over here we're taking the integral of 1, or the antiderivative of 1 with respect to dy. Antiderivative of 1 with respect to dy is just y, so that's where that y shows up. We also would have a plus c over here, but like I was saying, when we subtract that c from both sides, we still end up with some like c3 over here. So it's really this similar idea to what we've been doing, or rather, our old problems can be done this way as well. But the separation of variables piece allows us to do much more complicated problems. So let's take a look at another one of those problems. How about find the general solution of dy dx equals 1 over y. So we want to get all of our y's on one side, so I'm going to multiply both sides by y. And then I want to get all my x's on the other side, so I multiply both sides by dx. Now I can take the integral. So the integral of y is y squared over 2 plus c. The integral of 1 is x plus c. Now again, we want to get that y by itself. So I'm going to subtract this c from both sides. Let's call that c1 and that's c2. That's some other c. I'm going to multiply by 2. and plus or minus the square root again. And there we go. How about this one? For starters, let's find the general solution of y prime equals 4x cubed over 2y plus 1. Remember, the first thing we want to do is write it in dy dx form. Then we're going to multiply both sides by 2y plus 1 to get those y's over there. Then we're going to multiply both sides by dx to get the x's over on the right side. Then we take the integrals, or the antiderivatives, I should say. Okay, antiderivative of 2y is 2y squared over 2 plus y plus c. Antiderivative of 4x cubed is 4x to the fourth over 4 plus c. Those cancel out. Now notice we have both a y squared and a y, so we're not going to be able to solve for y in this particular equation. We can leave it in general form instead. General form means all variables on the left, all numbers on the right. So I'm going to subtract x to the fourth, and I'm going to subtract this c, c1 and c2, put them together in any combination, we just get another c. For part B, find the general solution of the same equation if x equals 1 and y equals 2. So what this means is solve for c and plug c back in. So what we're saying we've got y squared plus y minus x to the fourth equals c. We know that x is 1. We know that y is 2. So 2 squared is 4, plus 2 is 6, minus 1 is 5. And then we're going to put that back in. Right like that. There's one type of problem that shows up with particular frequency. Find the general solution to dy dx equals 3y when x equals 2 and y equals 1. This is something that's called directly proportional. It simply means that dy dx is something times y. And it involves an e and natural log. And so it's a little bit more difficult to work with algebraically, but it is very, very important to understand these thoroughly because they show up a lot. So it's already in dy dx. So we're just going to do separation of variables. I'm going to divide both sides by y. So we've got 1 over y times dy dx equals 3. Now multiply both sides by x. By dx. Now we can take the antiderivatives. Remember, the antiderivative of 1 over y is natural log of y plus c. Antiderivative of 3 is 3x plus c. And now we're going to solve for y. So first thing is we're going to subtract that c. Call it C3. And now the way that we can undo natural log is we can do e to the power of both sides. Now, the thing is that we can go further. We know our exponent rules. X to the a times x to the b equals x to the a plus b. So that means we can go the other way. Something that has addition in the exponent can be turned into multiplication. The convention is that we do this. And now we know that this constant is just some constant. So e to the some constant is going to be some number. We just don't know what that number is. That's going to be our next c. Convention is that we write this in front. Like that. Now, if x equals 2 and y equals 1, then we can solve for c. So 1 equals c to the 4th times e to the 3 times 2. So 1 is c to the c4, e to the 6th. Divide both sides by e to the 6th. That then goes back in here. Just like that. Let's do another one of those as a check for understanding problem. Find the general solution of dy dx equals 6y if x equals 0 and y equals 3. Go ahead and try that one on your own. Restart the video when you're ready. Pause the video now. Okay, so let's go over how to do this. So we want to separate our variables, so we're going to divide both sides by y. Then we're going to divide by dx, or multiply, excuse me. Then take the integral. So natural log of y plus c equals 6x plus c. Subtract c from both sides. Do e to the power of each side. Remember that adding exponents turns into multiplication if we write two bases. E to the c something is just some other number. And then we can come over and solve for c to the c4. Y equals 3, x equals 0. So e 6 times 0 is 0. Anything to the 0 power is 1. C4 equals 3. And there we go. Y equals 3, e to the 6x.